How many galaxies can be observed in the observable universe? The correct answer is about 200 billion. Now, imagine that we embark on an intergalactic journey that allows you to continuously translate from one galaxy to another within a second. The goal of this journey is to pass through all galaxies in the observable universe. Can you guess how much time it would take? The correct answer is 63 to 76 years, equivalent to the average lifespan of a human. However, this is just the observable universe. According to estimates by scientists, the part of the universe that humans can see only accounts for 5% of the total mass that the universe possesses. Previously, none of us could answer this question, even though determining the size of the universe is one of the most fundamental aspects of astrophysics. This inadvertently prompted scientists to delve into research to find answers. Until now, no one has dared to assert that current calculations are error-free. Scientists have dedicated half their lives to theories of time dilation, and the substance of the universe is also gradually being shaken. The truth about the vastness of the universe, whether it is infinite or finite, depends entirely on the foundational theories that we have long believed in. But what if Brian Cox suddenly denies that? Before the Big Bang, we had an ocean of energy, and the big explosion was just a coincidental shockwave that emerged, giving rise to matter. The universe existed even before the point in time when humanity believes it came into existence. Are we currently lost on the path to discovering the truth? What is the vast nature of this universe? Follow today's video to search for answers for yourself. What is the visible universe? First and foremost, let's clarify that the observable we're referring to here is not about the capability of human vision or technological advancements. Observable here is purely a principle, meaning beyond the specified range, we can never observe, regardless of how advanced our technology becomes. Based on the universe's expansion rate and the speed of light, scientists have determined the radius of the observable universe to be 46.5 billion light-years. Another slightly different figure is the observable universe from the time of the cosmic microwave background radiation, valued at 45.7 billion light-years. The mentioned figures mean that everything we can observe lies within a spherical region with a radius of 46.5 billion light-years from our location. Galaxies beyond this radius will never be observable because the light from them doesn't have enough time to reach us. In that colossal cosmic sphere, NASA estimated the number of galaxies using the Hubble Space Telescope, which has been in operation since 1990. In the late years of the 20th century, based on the collected information, humans initially projected around 200 billion galaxies in the universe. Using a new mathematical model, the research team calculated and inferred the number of hidden galaxies that even the most advanced telescopes currently cannot detect. About 90% of galaxies in the universe cannot be clearly seen because they are too faint or too far from our planet. Therefore, the number of galaxies in the universe might have reached 2 trillion by now, 10 times the previous estimate. According to scientists, the universe is continuously expanding, and our Milky Way galaxy currently has around 100 billion stars. If multiplied by the estimated 2 trillion galaxies, there would be around 200,000 trillion stars in the entire universe. Even this number might still be too small, as we may discover many more galaxies in the future with more advanced technology. With this scale, many people begin to believe that the universe is nearly infinite, or if it has some limits, it is still so vast that it's challenging to comprehend in relation to our existence. Until now, scientists have been striving to explore what can be found at the edge of the observable universe, wondering what lies beyond that can be observed. Are you curious about the galaxies existing in this cosmic void? Let me give you a little sneak peek into them. As of 2022, the farthest known galaxy is JD's GS's Z-Train 0, formerly GNZ11. JD's GS Z13-0 is a galaxy located in the Fornax constellation. In its name, you can see the character Z13, indicating that its redshift is 13, precisely 13.2. Thanks to Hubble's law combined with the influence of gravity described in the theory of general relativity, this value indicates that the light we receive from JD's GS Z13-0 originated just 200 million years after the Big Bang, meaning it took 13.6 billion years to reach Earth. In the sense that light took 13.6 billion years to reach Earth, this galaxy is sometimes described as being 13.6 billion light-years away from Earth. However, this number is not accurate because as soon as those first rays of light were emitted, the galaxy continued to move away very quickly due to the accelerated cosmic expansion. Currently, its actual distance must be 33.6 billion light-years. The distance, accounting for the shift due to the universe's expansion, is referred to as the comoving distance. This phenomenon holds true for many other galaxies as well. When you read that scientists receive light from a galaxy emitted 5 billion years ago, for example, in reality, that galaxy is now much farther away than 5 billion light-years. For galaxies nearby, the mentioned discrepancy is negligible, because at short distances, the expansion speed is much slower. A galaxy just a few hundred million light-years away, for instance, has a very low difference between moving distance and the direct distance from the speed of light. Galaxies even closer, like Andromeda, don't even require considering the comoving distance due to the universe's expansion. The cosmic expansion is strong at long distances, but at short distances it's minimal, so it doesn't override the relatively gravitational motion between galaxies. That's why, despite the ongoing expansion of the universe, Andromeda is gradually moving toward our Milky Way galaxy. So how do scientists predict the movements of galaxies? For example, scientists can simply shoot a beam towards the natural satellite of Earth, measure the time it takes for the light to touch the moon's surface, and bounce back to Earth. However, a similar approach cannot be applied when measuring distant objects in the Milky Way. Even with advanced technology capable of projecting extremely powerful beams, who could sit there for thousands of years waiting for the beam to return? Therefore, scientists have devised some tricks to try to measure the farthest objects in the universe. Stars change colors over time, and based on this clue, scientists can estimate the amount of energy and light they emit. Two stars with similar energy and brightness will appear differently in front of Earth's lens if one of them is farther away. A distant star naturally appears fainter. From there, scientists can compare the actual brightness of a star to what we see from Earth and use that difference to calculate how far away it is. Moreover, there's another, more universally applicable method for scientists to quickly estimate whether a galaxy is moving away or towards other galaxies. This tool is called the Doppler effect. The Doppler effect is a physical phenomenon in which the frequency and wavelength of waves, be they sound waves, electromagnetic waves, or waves in general, change when the source of the waves is in relative motion to the observer. Specifically, if a radiating source, such as a star, is moving towards an astronomer on Earth, its radiation wavelength will appear shorter, higher frequency, and thus higher energy. On the other hand, if the object is moving away from the observer, the wavelength will appear longer, lower frequency, and lower energy. You may have experienced a version of this effect when you hear the horn of a moving train or a siren as it passes by you, changing pitch as it moves towards and away from you. When an object is receding, meaning it is moving away from an observer, the peaks of the emitted radiation will be farther apart compared to if the source object were stationary. As a result, the light waves received appear longer. Astronomers say it is redshifted towards the end of the spectrum. Conversely, when a radiating source approaches an observer, the light waves appear closer together, effectively shortening the wavelength of the light. In terms of the spectrum, emission lines will appear blue-shifted towards the blue end of the spectrum. The use of Doppler shift has led to some significant discoveries in astronomy. In the early 1900s, it was believed that the universe was static. In fact, this led Albert Einstein to introduce the cosmological constant into his famous field equations to cancel out the predicted expansion or contraction in his calculations. Specifically, it was once believed that the edge of the Milky Way represented the boundary of the static universe. Later on, Edwin Hubble discovered that the so-called spiral nebulae that had perplexed astronomers for decades were not nebulae at all, but in fact other galaxies. It was a remarkable revelation, telling astronomers that the universe is much larger than they had known. Hubble then proceeded to measure the Doppler shift, specifically identifying the redshift of these galaxies. He found that the farther a galaxy is, the faster it is receding. This led to the famous Hubble's law today, stating that the distance of an object is proportional to its recession velocity. This disclosure prompted Einstein to write that adding the cosmological constant to his field equations was the biggest blunder of his career. However, the intriguing part is that some researchers are now reintroducing the cosmological constant into the theory of general relativity. It turns out Hubble's law is only accurate up to a point, as research in the past few decades has discovered that distant galaxies are receding faster than predicted. This implies that the universe's expansion is accelerating. The reason for this is a mystery, and scientists have given a name to this accelerating dark energy, considering it a cosmological constant in Einstein's field equations, although its form is different from Einstein's formula. Inflation and expansion accelerate. Many scientists are eager to uncover the truth about the origin of the universe or the nature of the accelerating expansion we attribute to dark energy. Going back to the initial topic, Brian Cox suggests, before the Big Bang, all that existed was non-time and an ocean of energy, almost still but gently rippling. He believes that initially there was an ocean of energy leading to the rapid expansion of space known as inflation. There were waves on the ocean. When inflation ended, the energy ocean from the Big Bang transformed into matter. At the very beginning, the constant in Einstein's field equations acted as the expanding substance, pulling everything apart. It wasn't created by the Big Bang. It has always existed there. In 2011, the Royal Swedish Academy of Sciences announced the Nobel Prize in Physics 2011 for 3 scientists, Saul Perlmutter, Brian P. Schmidt, and Adam G. Rees. They were individuals who carefully studied numerous supernovae in distant galaxies and concluded that the universe's expansion is accelerating. This discovery even surprised Nobel-winning physicists this year. What they observed is akin to throwing a ball into the air, and instead of falling back to the ground, the ball seems to accelerate faster and faster in the air, as if gravity no longer has the control to reverse the trajectory of the ball back to the ground. A similar situation has occurred for the entire universe. The increasing rate of the expansion process implies that the universe is being pushed apart by a form of dark energy hidden within space. Dark energy constitutes a significant portion of the universe, over 70%, and it remains the biggest mystery in modern physics. Cosmology underwent a seismic shift when 2 independent research groups arrived at similar results regarding the accelerated expansion phenomenon in 1998. Brian Schmidt led the second group, initiating the High Z Supernova Search Team (HZT) project in late 1994, with physicist Adam Rees playing a crucial role in this team. Both groups studied the universe by searching for supernovae, figure 2a, at distant locations, which are exploding stars in the cosmos. By determining the distance to these supernovae and their recession velocity, scientists hoped to uncover the fate of the universe. They anticipated that the universe was expanding at a decelerating rate, possibly leading to a balance between a big crunch and a big freeze. However, what they discovered was quite the opposite. The expansion process was occurring with acceleration. This isn't the first time that astronomical discoveries have overturned our understanding of the universe. Just 100 years ago, the universe was viewed as a tranquil entity, no larger than our Milky Way galaxy. The cosmic clock ticked steadily, and the universe was considered eternal. However, a fundamental shift occurred. At the beginning of the 20th century, American astronomer Henrietta Swan Leavitt devised a method to measure the distance to distant stars. Leavitt focused on studying pulsating stars known as Cepheids and found that the longer the period of pulsation, the brighter the star. Using this information, Leavitt could calculate the intrinsic brightness of Cepheids. If the distance to one of the Cepheid stars is known, then the distance to other Cepheids can be established. The dimmer the star, the farther away it is. A standard candle was born, and it became the yardstick for measuring the universe. Using Cepheids, astronomers quickly concluded that the Milky Way was just one galaxy among many in the universe. By 1920, astronomers, using the largest telescope of the time, Mount Wilson in California, found that most galaxies were moving away. They studied a quantity called redshift, which occurs when a light source is moving away from us. The wavelength of light stretches out and becomes longer, and the color of the light shifts toward red. Moreover, the farther a galaxy is, the faster it is moving away. This is Hubble's law. Thus, the universe is expanding. We know that the speed of light is the fastest in the universe. According to common sense, anything thrown out from the same explosion 13.8 billion years ago should not be more than 13.8 billion light-years away from us. However, reality is different. Thanks to the inflation of the universe and the continued accelerated expansion, the universe is much larger than 13.8 billion light-years in radius today. The universe is expanding faster than the speed of light. Over 20 years before Hubble's discovery, precisely in 1905, Albert Einstein formulated the theory of special relativity, in which he clearly stated that the speed of light is the maximum speed in the universe and nothing can surpass it. This is not a matter of technological limitations or how far scientific exploration has gone, but a natural principle. So, if in the far reaches of the universe, a galaxy is moving away from us at a speed greater than the speed of light, does it break Einstein's theory of special relativity? The answer is not at all. This doesn't contradict the theory of special relativity. It just clarifies its boundaries. To illustrate this, let's consider a small experiment that you can even do at home. Place an ant in the middle of a strip of rubber with one end fixed. The ant can move in any direction it wants on the strip with a speed of, let's say, 6 centimeters. Now, you can hold the fixed end of the strip and rapidly stretch it. The ant on the strip will immediately move away from both ends, including the fixed end and the end you're holding, much faster than its original speed of 6 centimeters, regardless of the direction it is moving. The issue is that it is unaware of this unless it observes both ends of the strip, as from its perspective on the strip, its speed remains 6 centimeters. The motion of galaxies, like all other objects in the universe, follows the same principle. The velocity of everything is relative to its reference frame, or more straightforwardly, the background it moves upon, similar to the path you walk on or the rubber strip of the ant in the experiment mentioned earlier. Einstein's theory of special relativity sets the limit on the velocity of any form of matter and radiation in the space-time background of the universe. However, it does not impose a limit on the expansion of space itself. Scenarios called the end of the universe. With the current increase in size and expansion speed, many scientists have contemplated scenarios for the universe's eventual demise. The first scenario is based on knowledge of thermodynamics. The heat death occurs when the temperature difference vanishes. According to the laws of thermodynamics, temperature differences transform energy, create work, and sustain the existence of everything. Once the universe reaches the point of heat death, all objects will reach the same temperature. Stars will die, almost all matter will decay, and ultimately, everything will turn into a chaotic mix of planets and radiation. Alongside the infinite expansion of the universe, energy will dissipate over time. Following the development of thermodynamics in the early 19th century, heat death seemed to be the most plausible scenario for the universe's demise. By the early 20th century, Albert Einstein's theory of relativity suggested that the universe might die in a much more catastrophic way. The theory of relativity posits that matter and energy curve space and time. The relationship between space-time and matter-energy determines the fate of the universe. According to this theory, the universe either expands or contracts. Since the universe has been and is currently expanding, the question is whether it will continue to expand and at what rate. The answer depends on the amount of matter existing in the universe. If the amount of matter does not exceed a certain threshold, the universe will continue to expand and end with heat death. If there is more matter than the threshold, gravity will be strong enough to pull everything back together, slowing down the expansion. However, if there is too much matter, the expansion will be replaced by contraction, and the universe will gradually shrink, becoming hotter and denser, ultimately dying in a self-crushing manner. This reverse scenario to the Big Bang is called the Big Crunch. The third hypothesis emerged at the end of the 20th century, following a groundbreaking announcement in the field of astrophysics. The universe is expanding at an accelerating rate due to the existence of a new form of energy called dark energy. Unlike dark matter, dark energy is a repulsive force, counteracting the gravitational pull between stars and galaxies, causing them to move apart. Currently, we understand little about this invisible form of energy. However, according to the scientific community, dark energy constitutes up to 70% of the energy in the universe, and this percentage is increasing every year. If dark energy continues to grow rapidly, in 20 billion years, it will be powerful enough to tear apart galactic structures, stars, planets, and even atomic structures. According to the Big Rip theory, 6 billion years before the universe's end, galaxies will be shattered. 3 months before doomsday, the solar system will disintegrate. And 1 second before the cosmic demise, every molecule in the universe will be torn into elementary particles. Moreover, dark energy possesses a peculiar property. Its density increases with the expansion of the universe. Concerningly, the case of dark energy's density rising faster than the universe's expansion is alarming. Robert Caldwell from Dartmouth College believes that it will transform into phantom dark energy, and the Big Rip will occur much sooner than our predictions. However, currently, the density of dark energy is still very low, much lower than the density of the Milky Way, where the density is far less than that of planets. The fourth scenario originates from the world inside the atom. This is considered the strangest and most abrupt conclusion for the universe. To illustrate this scenario, scientists conduct an experiment by pouring a type of pure water onto an absolutely clean glass and cooling it below 0 degrees Celsius. The water becomes supercooled and remains in liquid form, even below the natural freezing point. However, once an ice crystal falls in, the water will freeze rapidly because ice has lower energy than water. A similar phenomenon could occur in space, where the universe acts as a glass, and the supercooled vacuum is the environment. Everything will remain the same until a low-energy vacuum ball touches the vacuum's surface. The new vacuum type will transform the old vacuum environment. The vacuum ball will expand at the speed of light, and we won't be able to see it happening. In the new vacuum environment, everything changes completely. The properties of fundamental particles like electrons and quarks, the laws of chemistry and the formation of atoms all undergo transformations. Humans, planets, and stars will be destroyed in the big change. Dark energy will behave oppositely to its usual nature. Instead of tearing the universe apart, it will turn the scenario of the Big Crunch into reality. Fortunately, within the current understanding of scientists, there are no such vacuum balls. However, quantum physics asserts that vacuum types with less energy could exist. Thus, a vacuum ball containing this type of vacuum could be somewhere in the universe. Finally, as we conclude this video, I'd like to tell the audience that Brian Cox does not deny the Big Bang principle. Rather, he offers a unique and intriguing approach. Instead of denial, he proposes a creative story that has not been considered before, a narrative about existence before the formation of the universe. Brian Cox describes a pre-Big Bang state, a form of prehistoric existence, unlike anything we can comprehend. Through the combination of modern physics theories and unique creativity, he envisions a space-time where everything could originate from the transformation of energy and density. Cox is not someone going against the history of science, but rather someone presenting a new perspective, opening the door to the curiosity and artistry of scientific creativity. This video is not just an opportunity to delve deeper into the principles of the Big Bang, but also a challenge that encourages curiosity and research careers, expanding the boundaries of our scientific knowledge.